All right, hello everyone. Good noon. Saw the test grades, and it seems like the test grades on average are quite good. The average
Saw the
even
test grades,
before
and it
let me
seems
mute
like the
this.
test grade.
The average before any kind of curve is I think 81. I say curve. Before the makeup points is an 81. So, assuming everyone gets the maximum of 10 makeup points, um, that means the average will be 91, which is real high, but we're in trying times, so consider that just a little bit of an extra benefit. So hopefully that went well. Hopefully you all saw my email I sent out concerning just checking your own progress in the class, seeing where you're at, seeing if being able to make kind of wise decisions. So all the grades currently are up to date. Um, that means that I have adjusted all the quiz scores. Basically, the score that it shows right now for your grade in the class includes everything that we've been graded on, that I've graded you on up to this point, with the exception of lab grades, which I can't do until the very end of the semester. So you have to factor those in yourself. Um, and so that's all there. So you can see where you're at. Maybe you all also saw that so I also mentioned the idea of the satisfactory and unsatisfactory, and I've actually been notified that you all will make that decision, I believe, in the MyUCF. I'll double check that and send out an email just to clarify to you all where you'll decide that. But there'll be somewhere where you'll decide that, somewhere in MyUCF for each course, whether you want the letter grade or whether you want satisfactory or unsatisfactory scoring. You have some time in late April. Again, I'll send out an email with the exact details. But basically, I will submit all your scores as letter grades, and then the registrar office will go in and make the edits. So basically, if you have a C or higher and you chose the satisfactory or unsatisfactory, you get satisfactory. If you have a D or lower, that gives you unsatisfactory. If you have letter grade, it stays as it is. Okay. I also made an edit to the physics I care about. So reminder, physics I care about number 2 is due. So I actually shifted the due date to Monday, just because I didn't make any announcements about that. Want to make certain everyone gets that in. So you have Monday till Monday at midnight to finish that. Reminder that this assignment is just basically identifying something we've covered and how that connects to something that you're interested in. And again, this description needs to be more than just electricity makes this thing work. It needs basically a good rule of thumb for evaluating whether your submission is good is whether the explanation goes beyond what someone outside of this class could say. So someone who hasn't taken this class, you need to have something that goes beyond what they would be able to answer for this. So if you had been able to write your explanation before taking this class, you probably need to add more details. Um, and there will not be any additional curve on the test. There will just be the makeup points. That is the curve in some ways because, again, the average is very high for this test. So there's no need to curve anything. Um, okay, let's go ahead. Oh, one last thing I want to notify you all of. I'm going to try to do so. Reminder, all the lectures are here, which you're already familiar with if you're here. I'm going to start actually putting the title of the section, so it's just easier to locate appropriate material. I wasn't doing this before, but moving forward, I'll actually put the topic that's covered in that area. So with that in mind, inductors, I finished up last time, so we finished talking about inductors. And reminders that inductors is basically when you put a solenoid in a circuit. And the idea is when you put the solenoid in the circuit, the solenoid would resist high changes in current. So inductance is the characteristic of something to resist change in current. And so the consequence of all of this was that when you put a solenoid, anything is an inductor, but a solenoid is the one that pretty much we're going to be talking about. You put it in a circuit, we call this an inductor. This solenoid, this inductor will oppose a change in current. So to help, and I spent a little bit of time on this idea of this charging. Again, it's not literally charging. I'm using air quotes here just to, that's a how we kind of classify the cases. I spent some time on that, the idea of, okay, when I close the switch, it's going to current's going to initially be impeded, and then as time goes on, it's going to be allowed to flow because the inductor will oppose the large change in current. So I go from no current to some current, so it's immediately going to not want that. And then, so that was the charging case. And then the discharging case is when you disconnect the battery, current continues to flow. And so I didn't do as good of a job explaining this as I'd like, so I posted the simulation. So this, I'm going to go ahead and stop it and reset it. So I posted this simulation in the one here for March 27th. So it says inductor, lecture, clicker question, simulation. So you can find the link to this simulation and you can mess with it yourself. But the part that, so this simulation has the charging and discharging case. So if I go ahead and stop it again, reset. Okay. So right now, nothing is flowing through here. So I can even, well, unfortunately I can't connect to that one. So no current is flowing. But you see here, the second I start it, you're going to notice that current goes slowly. It's slowly, and then it starts increasing in speed, increasing in speed. And you can actually see here on the bottom, a graph of voltage across the inductor with respect to time, and a graph of current in the circuit with respect to time. So you see the current started at minimum and then increased until it reached a maximum, which is this flat line. And then it's just going to kind of stay here forever. And this maximum would be the voltage of the battery, which is, you can see here, 5 volts. It's at VD. Unfortunately, I can't move my mouse down to see it, but if you look in the bottom right, it says 5 volts. And the resistance is 140 ohms. And so you could calculate the current by doing 5 divided by 140. Okay, so that's the charging case. Now, you're going to see here, when I switch it, so I'll stop it right now. When I switch the circuit here, I have now basically disconnected the battery from the circuit. The battery is no longer going to be, because there's an open path here, so the battery is doing nothing, so our circuit is basically just this right side. And you're going to see here that current actually continues to flow. Current continues to flow, so it actually goes a max, so it stays at maximum, and then it decreases with respect to time. So, putting these two together, you see current slowly starts increasing. That yellow bar here on the bottom starts slowly increasing because the inductor opposes that immediate change, and then that change gets less, so it opposes the current less. And once I switch this, you see current continues flowing in the same way because the inductor is the one pushing the current because it sees, oh, there's no battery pushing it anymore, but I want to keep the same current because I want to keep the same flux. And so it pushes that current through it in the same direction, but it loses energy as time goes on. It loses that energy in the resistor. And so that's why eventually we go to zero current, zero voltage. So we start here, current slowly builds up, reaches a maximum. And then at any time we can go ahead and switch it. And you're going to see current's going to kind of stay the same. We'll close this down so you all don't see that. That's just for my research stuff, so just to not distract you all. And then it kind of slows down. So play with this. If the idea didn't make sense, I want you all to spend some time on that. Okay, today, so spend a few minutes on that. But today we're actually going to be moving into AC circuits. So AC circuits, this is the second to last section we're going to cover. We have AC circuits, and then we have optics after this, and then we're done. So AC circuits is alternating current circuits. So circuits with a current that's alternating, and we'll talk about what that is. So these are the main things we're going to be covering. We're going to talk about what alternating current is, what alternating voltage is. We're going to talk about features of this alternating current and voltage, as the amplitude or peak. We're going to talk about resistors, inductors, and capacitors behave in these circuits. We're going to talk about impedance. We'll define what impedance is in an AC circuit, and we're going to talk about the power in an AC circuit, how power is dissipated. These are all the 4 main points. Okay, and previous concepts that we've covered that are going to be relevant for this is resistance, so resistors, capacitors, inductors. So we just covered inductors, and then capacitors and resistors we covered before. They were on the last test, so hopefully you're familiar with those. Voltage, current, and then frequency and angular frequency, which are two different things which we're going to make certain to clarify the differences between. So immediately jumping into it, alternating current means that voltage and current vary with time. If current varies with time, voltage is going to vary with time. If voltage varies with time, current varies with time. They're linked together. Remember, by that Ohm's law is kind of the easiest way to show that. And so on the bottom left, we have what voltage looked like in our DC circuits. So this meant we just had a battery. So a DC circuit was literally just like a battery and a resistor. This was DC circuit. Now we're going to talk about AC circuits, which means we have some AC voltage supply. This is the symbol for it. It's just this kind of squiggly in a circle. And this can be hooked up to all sorts of things. For simplicity, I'm just going to put a resistor. And so you can see here the voltage is varying with time, and it's pretty much always a sine wave or a cosine wave. We're going to specifically just say sine wave. And you can see here sine wave starts at 0, increases to maximum, and then decreases. And so this is time on the bottom. This is the equation for it. So the equation is the voltage with respect to time. So the value of voltage here is going to equal V naught, where V naught is the maximum voltage. If we look at our graph here, V naught is the peak amplitude. So that's the amplitude of our wave. Omega is the angular frequency. Angular frequency is radians per second. You have to be very careful here to use angular frequency, because on the next line, you see I introduced just regular frequency. Frequency, the variable for that is F. Angular frequency is omega. So that's omega. That's just the Greek letter omega. The conversion between the two is omega equals 2 pi F, because the idea here is 2 pi is how many radians there are in an entire period. So 2 pi, so I'm basically just multiplying frequency by the radians in an entire revolution. And you have to be very careful, because these both have the exact same units of hertz. And you may be confused, because I said here radians per second. I'll tell you frequency is revolutions per second. Revolutions per second. And I'll move this thing down. And the idea here is the reason we don't see those. Yep. The reason we don't see radians in this hertz and revolutions in this hertz is radians and revolutions don't have a unit associated with them. Radians is not there's no SI unit for radians, there's no SI unit for revolutions. So that's why you end up getting hertz. Hertz is just seconds inverse, which is just 1 over seconds. So the SI unit for these is 1 over seconds. And so that's why they have the same unit, because it's radians, revolutions, but they're different. In a problem, if I ask you for angular frequency, make certain you give me angular frequency and not frequency. If I ask for frequency, make certain you give me frequency and not angular frequency. All this means is that if you solve for frequency and I asked for angular frequency, multiply frequency by 2 pi. If I asked for angular frequency, or if I asked for frequency and you solve for angular frequency, divide angular frequency by 2 pi. Very simple conversion. Make certain you do it. This matters. We have to put the right thing in there. The reason is we have to have in this. If you're taking sine of something, it has to be sine of an angle. And radians is an angle. Revolutions is not an angle. So you have to have that angular frequency in here. Otherwise, you don't get the right answer. Okay. So, big takeaways here. Angular frequency is omega. This is V naught. And so the next question is, this is one of the quicker questions I'm asking for you all. Where I give you that equation. I give you voltage equals 10 times sine of 5t. And I ask you for the frequency. Frequency, not angular frequency. So what you're going to do when solving this problem is you will just look at the form here, V of t, the voltage with respect to time equals V naught sine of omega t. You see here I give numbers, so you need to just figure out which of these corresponds to angular frequency and then convert it into frequency. Okay. Okay. I will go ahead. Yeah. This is, I guess, a decent time for a break because it's something where I want you all to think about it. We haven't gotten too far, but that's because we spent some time on the inductors. And so the break, feel free to ask me questions. I'll hang around. Again, we'll just make it short, a couple minutes. And I want you to think about what is the average value of a sine wave from 0 to 2 pi. If you have any questions, let me know. I can go grab my dog. He's not in the room right now, but that'll give me something to do in the 2-minute break as well anyway. So. All right. Oh goodness, I always have to see. Right. And there's the dog. Somehow, that's him. It's very hard to direct this thing when I can't see it. But there you go. There's our daily break of Buster. He does not smell very good right now because he was outside. Ooh, don't smell good. All right, so moving onward, short break, but didn't see any questions. What is the average value of a sine wave from 0 to 2 pi? So let's go ahead and just draw a sine wave. There it is. What's the average value? Well, the average value equals 0. So if the average value is 0 here, because right now, why am I even talking about this? Why are we talking about the average value of this sine wave? Well, if we think of, so it's 0, because for every positive value here, there is a negative value, which is exactly the same, but it's negative. So if this point is 3, there's a -3 here. And so if you took the average of every single, so if you took all the numbers here, there would be numbers here, because remember the average is basically taking every single value, adding it up. So you almost like imagine bending this into a bunch of pieces. Take every single value and divide it by the time here. So normally if you did this, you would actually do an integral, and it would be the integral from, we'll say this is 0, and we'll say this is capital T. So 0 to t, v of t dt, actually, sine of whatever, we'll just say omega t dt, 1 over t. This is the equation for finding the average over anything. But you can see here, for every value here, there's an opposite value here. So if you took the average of this, it would end up being 0. Kind of similar, if you took this integral, that's another way to think about it. If you took this integral here, the integral is the area under the curve, so you would get some positive area here. You would get the exact same negative area, which would end up canceling completely. So this integral would end up just being 0, which equals 0. So if that doesn't make sense, I recommend kind of looking at it a bit more in your own time. We're not going to spend too long there, because what I want to emphasize is, why do we care? Why are we trying to find the average value? Well, if you think about an AC voltage, I can't just say the AC voltage is a certain number. So for instance, say we're like, oh, let's choose the amplitude to characterize it. Say we have an AC voltage of 5 volts. Well, that tells you the peak, but what if this thing's oscillating really quickly? So maybe it's actually more useful for us to think of the or we want to also recognize that it goes up and down. So figuring out an average value would kind of be a more useful way to characterize this rather than just a peak. Just another way of thinking about it. But you can see here, if we literally just took the average, so if we go back here, if we just took the average of it, you get 0. So that's not very useful because no matter what voltage source you'd have, no matter its frequency, no matter its height, you get a voltage, an average of 0. So that is where we get this thing here. So we saw in the title, this RMS. This is the root mean squared. And so the idea here is instead of taking the average, just the regular average, what we will instead do, and let's see if the next slide actually shows this good. What we instead do, so if we have it here, here's what it looks like. We square it. And what that'll do is it'll make all the values positive. So by making all the values positive, you can actually get an average value. Okay? So the way to do that is, remember when I showed you all the average here was 1 over the length of it, the period is what we call that, times, or taking the inner side. So if you just squared that inner side, and I guess just to make it match better, let's put that V naught there. You square it, so V naught squared, sine squared, 1 over the period still, and you square root all of that. So literally root mean squared it's the square root of the average of a squared function. So there you go. And when you actually do that, you get this really nice solution, which is that this root mean squared, even though it looks like this crazy function, no matter what, if it's a sine wave, it is just the amplitude divided by square root of 2. So this is just a useful, and this is interesting because it actually doesn't matter what the angular frequency is. So this is just another way of characterizing an AC voltage source. You still do have to report the frequency because that could be useful. So for instance, our wall sockets, I believe, have, oh gosh, I'm going to mess this up because I think it's like 120 volts and I believe it's 60 hertz. And that's the frequency, that's not the angular frequency. So our wall socket, this would be 120, and then this would be 2 pi times 60. But this RMS, this root mean squared, is something you'll sometimes see. Instead of the maximum being reported, they'll give you the root mean squared. Just another way of thinking about it. Okay. Interestingly, if you actually took the absolute value of it instead, so we squared it. If you instead took the absolute value of the function, it gives you a slightly different answer. And here's one of the reasons we use root mean squared. That's actually practical. I'm not going to test you on this, but it's just like, okay, why do we care about root mean squared? Why not just use the maximum? The root mean squared gives you the, if we had an AC voltage supply with a resistor compared to a DC voltage supply with a resistor, the root mean squared voltage of that AC circuit allows us to basically imagine if we built a circuit like this, this would be V naught square root of 2, and the power dissipated in this, power 1, power 2, power 1 equals power 2. So if we built a DC circuit and we wanted to dissipate the same amount of power as we did in the AC circuit, the power dissipated in that would be the same if the voltage source is the value of the root mean squared, the RMS voltage from the AC source. So just kind of an interesting thing. Why do we care about RMS? It's because it gives another way to interpret it in a way that's kind of a bit more easy to think about, that if we could easily then calculate the power here if it was just a resistor. So the next question I ask you all, what is the RMS voltage for a voltage supply given here? And so you're going to do the same thing. So remember that V equals V naught sine of omega t. And then you just have to go to the slides below and remember that the root mean squared is just this divided by square root of 2. I'm not going to write that down because I want you all, I'll go back here and show it, but I don't want to make it too obvious when you all do this again. Root mean squared equals the voltage V naught divided by square root of 2. So identify V naught in this problem, divided by square root of 2. Pretty straightforward. Okay. This is going to kind of be the last bit we're going to talk about today. And so in AC circuits, capacitors and inductors are going to behave differently than they did in DC circuits. They're going to behave the same conceptually, but before, so let's just kind of walk through the capacitor case and you'll see what I mean. Here is, remember, the DC case of the capacitor. So if I close switch A, I'm going to put a blue pin instead of a, that's still not easy. Let's make it red. Red will stand out. If you close switch A, when is the current going to be maximum? So this, and let me check if the next slide has these answers. It does not. Remember that in a DC circuit, the current was maximum initially because as time goes on, so this is where, if this isn't, this is kind of a review. As time goes on, current goes like this. That means I build up positive charges here. At some point, these positive charges will build up. As they build up, they're going to oppose more charges getting on them. If they're opposing it, almost imagine it like a pressure kind of thing. You're inflating it. The more you inflate it, the more it's kind of pushing back. The more current, the more charge that's here, the more it's opposing more charges getting added to it. Until eventually this is fully charged and the current is 0. So this means that a capacitor, capacitor opposes current the more it gets charged. So the more charge that you get on the capacitor, the more it's going to oppose current. So initially it doesn't have any, so it doesn't care. At the end, it's maximally charged, it cares a lot. All right, so once they're fully charged, there it is. So this means, and this is kind of the really weird part, that in an AC voltage supply, so an AC voltage where the voltage is going up and down, this voltage is kind of where current is flowing. You see here that the current is not in the same, we call this phase, as the voltage. The maximum of the current actually occurs before the maximum of the voltage. Okay, so just for a quick comparison, here's what it looked like when they're in phase. If this was just a resistor, the current is the maximum and the voltage is the maximum. Same time. But with a capacitor, the current is actually maximum before the voltage gets maximum. And the idea, and this is the, to specify, this is the voltage across capacitor. This isn't the voltage of the power supply. This is the voltage across the capacitor. And the idea here is that, let's look at current here. As long as current is positive, let's just define positive as going clockwise. Positive voltage. And we'll define, so this is positive voltage, and we'll say that negative voltage is the other way. Or negative current is the other way. That's a better way of putting it. Positive current is that way, negative current is that way. That's what the difference in sign means. It means the direction is shifted. This is not a hard set rule that clockwise is positive and counterclockwise is negative. You just have to, I'm just defining that here, but that's not a set rule. But as the current is positive, so in this beginning section here, as the current is positive, that means I'm pushing positive charges onto this. As long as it is positive, who cares what value it is, as long as it's positive, I'm pushing more and more and more and more charge on it. The second current switches to negative, the charge is now going to leave and go the other way and start building up on the other side. Okay? So when it's positive, it's building, building, building. Once it switches, it's going to start building up on the other side. And so let's see if this makes sense. So as long as it's positive, I'm going to get more and more and more charge. And so my voltage, remember, voltage across the capacitor. So C equals Q over V. So V equals Q over C. So the more charge, the more voltage. So the more charge I push on it, the higher the voltage. As I start to lose charge, I lose voltage until at some point, I am now, instead of canceling out the negative charges on this side, so if we imagine there's positive and there's negative, instead of canceling out negative, I've canceled out all the negative and now I add more. And so then you start getting a buildup of positive charges on the other side of the capacitor. Again, the same thing until the current switches, at which point it changes. And so this just keeps going. So that's the idea behind it. But the big takeaway here is that the voltage in a circuit with a capacitor, the voltage across the capacitor lags behind by 90 degrees. To clarify, you may wonder, isn't it the current that's behind it? Because the current's to the left of it. Remember that time increases to the right. So this occurs first. Points on the left occur before points on the right. So this happens first. It has a maximum current. Then later it gets a maximum voltage. So that means that the voltage is behind it. It occurs later. And yep, you see here we get this additional... So this is very similar to our one with our voltage equation, except now it's current with respect to time. It's still a sine wave. And you see here we get, it actually shifts by that 90 degrees, by that plus pi over 2. Okay. Whew, sorry, that was a lot. But just, I would recommend kind of take some time, think about that. I'll try to find some animations to help clarify that. That'll kind of visualize it, and I'll show those next class. But the last thing I want to quickly clarify is, so previously we just talked about resistors resisting current. In AC circuits, resistors, capacitors, and inductors, we think of them all as opposing current. Just like we saw here, you saw here that the current is changing. That means it is opposing the current. And so in an AC circuit, we actually use this thing called reactance. And reactance, you're going to see here, look, the units are ohms, which basically means that reactance is just like resistance. So how much a capacitor opposes current in an AC circuit, so a capacitor, it's called capacitive reactance. It's analogous to resistance, and this is the value of it. It is this capital X subscript C for capacitor equals 1 over the angular frequency. And you may ask, is it the angular frequency of voltage or is it the angular frequency of current? They have the same one. The angular frequency of voltage will be the same as the angular frequency of voltage. If we looked at the last graph, you see here they occur at the same frequency. They're shifted, but they're still kind of matching the peak here. The periods are the same. The distance between these two peaks is the same as the distance between these two peaks. All right. So that is basically everything we're going to cover today. This is the angular frequency. So you would just literally, if you had a circuit with an AC power supply and you had it hooked up to a capacitor, so you would get some voltage equation. Voltage with respect to time equals V naught sine of omega t. And so this is the capacitance. So if you wanted to find the reactance, X of C is going to be just 1 over omega times C. And this is the last thing I want to clarify that's really interesting. Remember V equals IR? Well, turns out if you just have a capacitor, V equals I times XC. If only capacitor and circuit. We'll talk about what happens when you add more elements. There's ways to add those up to get this. That's what impedance is. But this is where it's really interesting, is that now we actually start to treat these elements all as resistors. Okay. So, this kind of concludes it. This is the last clicker question I gave you all to answer. It says, what is the maximum current in a circuit where the voltage is given by that same form we've seen over and over again? And we have a capacitor with 8 microfarads. And so you're going to use this exact process I kind of outlined here. Find that how much the capacitor resists the current. Find that capacitive reactance using this equation. And then you know the voltage. What's the maximum current? Well, it's going to be when you have use that maximum voltage. Okay. All right, so that concludes it for today. I do not have a clicker question video for today because there's no clicker questions to solve at this point. So that ends my streams for today. If you all have any questions, again, please feel free to email me. I've contacted the grader about grading the makeup points, and those should be done hopefully in a week or two. I'll let you know more details once I hear back from them and hear what time frame they think for that. For the makeup points, you have to actually find the correct answer on your own and show the correct work to get there. I'm not going to give you the correct answers. Will be posted today at midnight. You'll be able to go back to the test and see the correct answers. And that's why the makeup points are due tonight by midnight. Because you need to identify what the correct answer is and actually how to get to it. Because the goal of this is to see if you actually then, okay, you missed the question. All right, what did I do wrong? What's actually the correct answer? So hopefully that answers your question, Aaron. If you have any, if that doesn't clarify it, please email me. All right, have a good rest of the day and a good weekend.